Hey everyone, and welcome to this explainer. Today, we're diving into what I like to call the concrete water paradox. If you're in the industry, you already feel that constant tension between getting a mix that's super strong and a mix that you can actually work with. But the microchemistry behind that trade-off, it's actually deeply misunderstood. So we're going to completely reframe how you think about hydration versus workability.
So here's the big question. Why does adding water to concrete actually destroy it? I mean, picture a busy job site. We usually just assume that bumping up the slump by tossing a little extra water into the mixer is a total win. It makes the concrete soupier, easier to pump, and way faster to pour into all those complex forms. Seems practical, right? Well, actually, that innocent splash of extra water is a hidden structural disaster. We're literally sacrificing decades of durability just for a few minutes of placement convenience. Let's look at why.
Section 1, the water of convenience. To really grasp this, we gotta zoom way in and look at the microscopic level the exact second cement and water meet. It turns out we're actually dealing with two totally different types of water in our mix. First up is the water of necessity. Cement absolutely needs water to hydraulically activate. When they mix, they trigger this complex chemical reaction that grows these tiny calcium silicate hydrate, or CSH crystals. These little fibrils branch out, interlock, and build that dense, rock-hard matrix that gives concrete its massive structural strength. But here's the wild part. That chemical magic only requires a water-to-cement ratio of exactly 0.25. That's it. But try pouring a 0.25 mix by hand. It is unbelievably stiff. So to actually get the job done, we add what we call the water of convenience. This is extra, free water added purely as a physical lubricant. It pushes the cement grains apart so the mix flows better. But chemically, it does absolutely nothing. It just sits there.
Section 2, evaporating water leaves voids.
Okay, so follow the timeline here. First, we add that water of convenience just to make things workable, suspending all that heavy aggregate in a fluid state. Second, the concrete sets. Those CH crystals grow and lock everything down, but they're basically building a rigid cage right around those pockets of unused free water. Third, over the next few days, weeks, or even months, physics takes over. That trapped water naturally evaporates, slowly making its way out of the slab and into the air. And fourth, and this is the fatal flaw, guys, when that water leaves, it leaves behind permanent, empty, microscopic voids called capillary pores. Since the concrete is already rock hard, it can't shrink to fill those gaps. The voids are trapped in there forever. So you haven't poured a solid rock. You've basically poured a rigid sponge. The more water of convenience you dump in today, the more empty space you leave inside your structure tomorrow.
Section 3, dropping compressive strength.
And the numbers on how these voids ruin long-term durability are honestly staggering. Let's say you have a tight 0.30 water-to-cement ratio mix. The cement grains are packed super close together, creating a really dense matrix. By day 90, you're looking at a massive 72.5 megapascals of compressive strength. But if you bump that ratio up to 0.60 just because it's easier to pour, your matrix becomes totally riddled with those empty capillary voids, and your strength plummets to 34.2 megapascals. You're losing more than half your strength. Literally, every 0.1 increase in your water-to-cement ratio strips away 15 to 20% of your structural integrity. When a heavy load hits that porous concrete, those tiny air pockets give zero pushback. The material just fractures internally and crumbles under the pressure. Section 4, increasing chemical permeability. And it gets worse, because we're not just talking about bearing heavy loads. Those capillary pores essentially act like an open highway for environmental destruction. Because that extra water evaporated and left behind an interconnected network of tiny tunnels, your concrete's permeability goes through the roof. A low water mix, like a 0.35, is practically an impenetrable shield. It keeps the internal steel rebar completely sealed off. But a 0.50 or 0.60 mix, it acts exactly like a wick. It sucks in moisture, pulling in nasty stuff like winter de-icing salts or harsh marine sulfates deep into the slab. And when those chemicals hit the reinforcing steel, the rebar starts to rust. Now, rust can expand up to 6 times its original size, which creates this immense internal pressure that physically cracks and blasts the concrete apart from the inside out. You're literally rolling out the red carpet for the elements to rot your structure. Section 5, the consolidation solution. So this brings us right back to our ultimate paradox. We absolutely know that extra water ruins concrete, but we still desperately need a mix that can flow through tight forms and heavy rebar. So how on earth do we fix this without grabbing the hose? The answer is mechanical consolidation. Instead of water, professionals use an internal vibrator. Think about internal friction for a second. In a stiff, low-water mix, the jagged edges of the sand and gravel are all locked together. It won't flow. But when you plunge a rapidly oscillating vibrator into that mix, pulsing at something crazy like 10,000 vibrations per minute, that kinetic energy aggressively breaks the friction. The aggregate literally bounces apart. For a few magical seconds, the concrete temporarily liquefies. It flows laterally into every single corner of the formwork, wrapping perfectly around the rebar, and it does all of this without needing one single extra drop of water.
The visual difference when you do this right is completely night and day. If you want those flawless, towering architectural finishes, you consistently use a stiff, low-water mixture and consolidate it perfectly with vibration. That mechanical action physically forces all the trapped air bubbles up to the surface and packs the heavy aggregate down into this tight, incredibly strong finish. But compare that to taking the easy way out. When you just dump in excess water for convenience, the heavy aggregate sinks, and the lighter water forcefully bleeds right to the top. What you're left with is a weak, highly porous, sand-streaked surface skin that's just begging to crack, scale, and dust away. The visual evidence of a compromised structure is impossible to ignore.
Okay, let's wrap up the real power of choosing mechanical consolidation over liquid convenience. Number one, it completely replaces the need for extra water. You're using kinetic energy to do the heavy lifting instead. Number two, by breaking that internal friction between the rocks, you get the exact flow and workability you need for complex pours. Number three, and this is the big one, because there is no excess free water just sitting there waiting to evaporate, you completely prevent those structural capillary voids from ever forming. You're leaving behind nothing but pure, dense, hydrated cement. And finally, because everything is packed so tightly, you maximize your compressive strength and build a nearly impenetrable fortress against massive physical loads and chemical attacks.
Which leaves us with one final, pretty important question to think about. If ultimate strength and durability rely on using less water, are you vibrating your concrete enough to protect its future? Next time you see a truck rolling onto a site, remember the paradox. The easiest pour today might just be the fastest collapse tomorrow. Keep this fundamental science in mind on your next project, and you'll be building resilient structures meant to truly stand the test of time. Thanks for hanging out with me on this explainer, and as always, keep questioning the science behind the everyday world around you.